Sim. Bem-vindos a... Provavelmente vai ser o último colóquio.
Sim, desse semestre.
O último colóquio, sim. Primeira coisa, o colóquio vai ser gravado, como em todos os colóquios. Se você faz perguntas, você aceita que a sua pergunta vai ser gravada. Hoje temos a honra e o prazer de ter Igor Shovkovy. Ele nasceu a 30 quilômetros da um outro ucraniano, um certo Gleb Vatagen, que alguns de vocês poderiam conhecer. Estudou física na Taras Shevchenko, Universidade Taras Shevchenko em Kiev. Depois fez doutorado em Cincinnati, na Universidade de Minnesota, com Jokapust, alguns de vocês conhecem o livro. Depois ele foi para Frankfurt e agora ele é professor de física na Universidade de Arizona, não essa aqui, a outra, em Phoenix. Essa aqui foi doutorado. Ele tem uma grande variedade de interesses, trabalhou no grafeno, trabalhou um pouco, interagiu com Yakov Kotelevich, que você conhece, trabalhou com grafeno e com semimetalos, trabalhou sobretudo com utilidade do Quark, sobre quarks, matéria de quarks em campos magnéticos e teorias de campo em geral em campos magnéticos. E agora tem essa aplicação na astrofísica das partículas. Vai falar disso.
Thank you so much. It's my great pleasure to be here. I'm here for the first time in Campinas, and it's my great pleasure. Giorgio Carriere was inviting me to come here for many years, but there were no good opportunity until recently, and I'm really very glad that I accepted this invitation. It's very nice, beautiful here. Very glad to see a lot of people who are interested in all kinds of physics. I should probably give you a disclosure before I start. I'm working as a theoretical physicist, trying to apply quantum field theoretical methods to different fields of physics, ranging from heavy ion collisions to quark-gluon plasma in different environments, including quark matter in stars. I'm definitely not an astrophysicist, and there are probably people in this audience who know physics of neutrinos, astrophysics better than me. And I'm going to talk briefly about the general understanding of the systems that I'm going to talk about, neutron stars, magnetars, and try to be very general. And as soon as you have any questions that something seems unclear, please feel free to ask. I would be more than happy to answer to the best of my ability. With the hope to come later of the talk to approach the original results that my postdoc and I obtained this year, and this has to do something with the quark matter on the extremely high densities and in the presence of strong magnetic fields, which is actually applicable potentially to the interior of magnetars, very exotic types of neutron stars that potentially carry quark matter inside. So to start this journey, I'm going to briefly introduce the idea of neutron stars. Neutron stars, of course, considered to be very interesting from astrophysics point of view. From me personally, this is actually perfect laboratory for studying dense quark matter. Generally dense matter, I should probably say, and in general under extreme conditions that may include not only the density, but as I will explain later, also magnetic fields. The idea of neutron stars dates back to roughly 1930s. This is one of the published papers, which is considered to be the first theoretical foundation in publication. There are some ideas, some rumors that idea about this kind of stars was also presented by Landau unofficially, and it wasn't published as far as I know. But what's interesting about this is essentially that this is a quantum, very original state of neutrons, that you pack under large compression in the center of the star. So this is not just a regular state of matter because it necessarily involves this degenerate state of neutrons. So that's where the idea was expressed theoretically, and in 1967 to be precise, this was detected, the paper was published a year later, but this was detected in astrophysics observation, where it was noticed that certain objects in the universe, they are essentially beeping, literally beeping in radio, with radio signals, and that beeping is coming very rapidly with a period of sometimes as little as milliseconds to maybe a couple of seconds. And this is repeating all the time. So these are not little green men signaling us, it's actually some objects that are rotating. And in fact, in order to rotate with that kind of frequency to provide the signal every second or even multiple times per second, it has to be really, really compact. So that's actually where it kind of comes together, that it has to be compressed to such small size that it has to be a neutron star. The radius of that star should be not much more than roughly about 12 kilometers. In fact, if you take any other compact star of a different type, for example, white dwarfs, which are not made of this kind of exotic matter, then you will see that those have radii thousands of kilometers, and obviously they would not be able to rotate so fast. And you probably know why, because if they do, these particles on the surface will be moving faster than the speed of light. So that's definitely impossible. This has to be really compact. Now, as I said here, they are pulsating, and they are pulsating because there is something else is happening there. They must carry some magnetic field, and this picture is illustrating, actually movie is illustrating you roughly why do we see those pulses when this beam is sweeping the line of direction, line of sight, and you're looking at that from that point of view, you will see essentially a signal coming, and that's going to be essentially that pulse that you observe. And then, of course, it's rotating, so essentially for each full rotation, you get sometimes two pulses, one if only one of this is pointing in your direction. And that's essentially what they call the lighthouse effect from the pulsars. So, two general messages: pulsars are neutron stars, they are really compact, and they are really compressed. There are a lot of different observations of pulsars, and to date, there is more than 3,000 pulsars observed or detected. And this conventional diagram, the so-called PP dot diagram, which essentially shows you the period versus the period derivative, or P and P dot, shows essentially all of those, actually probably not all of those, because this is already nearly a 10 years old graph, and each of those points is representing a pulsar. Considering just those two simple observables, the period and period derivative, you could actually extract a lot of interesting, although not very reliably, but a lot of interesting characteristics about this star. So this ratio, which has the units of time, will give you tentative age of the star. And those lines across are showing that the younger stars will be somewhere closer to the top, the older stars will be closer to the bottom. You could also consider how luminous they are, how much energy they are emitting, also considering that they are losing their rotational energy, how much of the energy they carry. You could calculate roughly like with any object that you're swinging, like a rock on a string. And you could calculate how much energy they're losing, and in fact that energy also changes roughly along these lines. That's a constant energy lines. And similarly, you could also make some assumptions about the physics that is happening there and estimate how big or how strong the magnetic fields are in those stars, actually on the surface of those stars. And you could see that there is a wide range of the magnetic fields that is ranging from something relatively small on the order of 10 to the 8th Gauss up to more than 10 to 14 Gauss here. And those stars shown there on the graph, actually not stars, triangles on this plot, they're representing magnetars. I'll briefly mention about the magnetars a little bit later, but essentially those are the stars which are strongly magnetized. If you look at the neutron star and try to theoretically consider what's happening in the interior, you will immediately come to the conclusion that because of their compact size and the mass that is relatively large, it's essentially larger than the mass of the sun that we are orbiting around, then you could understand that the compression of the matter is extremely high in the center of the star, and it could be reaching up to 10 times the nuclear density. So if you take some nucleus, I don't know, uranium, and consider what's the density of that nucleus, this would be roughly 10 times larger than that. This is extremely large density, obviously, and to give you sort of flavor how bad that is, or how strong that is, how large density is, you take just a spoonful of that matter, it will be roughly the weight of a mountain. That is the size of like 1 kilometer, 1,000 meters high. So, what is the state of matter inside of that star is actually a big question. Clearly, we cannot just take a little piece of that material in the lab, measure it, and be happy. It's not present anywhere around. So, you do theoretical calculations, some modeling, do the best you can, and this is the consensus about the structure of the neutron stars. At the surface, there is a tiny layer of atmosphere, and literally it's about that thick, maybe the width of my finger, mostly made of hydrogen. There are some other light elements, but pretty much that's it. The outer crust is neutron-rich nuclei, so essentially think of something like, I don't know, iron. This is also relatively thin, maybe 100 meters or so. Then, of course, you get to something a little bit more interesting, something that is essentially heavy nuclei with some neutrons that are starting to drip out of it. Think of it something like a sponge, where you take the sponge, that's your nuclei, which is wet, and you start squeezing, and that water is like neutrons starting essentially dripping out of it. So that's that matter. There are too many neutrons. They are still around, basically working like a glue between the nuclei, but essentially they are free. There are too many of them. They cannot be bound in those single nuclei. When you compress it even further, something dramatic happens. The protons inside of the nuclei, they actually don't like to be compressed so much. In fact, they try to go into something else. But there is a problem. The protons inside the nuclei, they are repelling each other badly, and they don't want to go any closer. If you insist, those protons have to convert into something neutron. They actually go the weak process and turn into neutrons. And essentially, that's how you create a nuclear matter that is essentially most of the thickness of the star, presumably. At the very core of the star, there is a possibility, and I should say it's only a possibility. We don't have very reliable information that it might be the case, that state of matter may be still something else. Of course, the simplest possibility that it's still nucleons, just compressed too badly, but then it could be also some exotic hyperons, some condensates of mesons such as pions and pions and stuff like that. But it could be also, and it's probably the simplest of all, possibility of quark matter, where essentially you compress the nuclei so much that essentially now the quarks start dripping out. They basically become deconfined. And that's the state of matter that I will be primarily concentrating on this in this talk. It's also very important how we know that information, or how we deduct that information from the theoretical calculations and the observations. So one way theoretically to predict what's happening in the star is consider something very simple. How this star is formed if you start adding there layer by layer by layer. In the end, you pile up so much matter that it gets compressed by gravity. So how it works and how it stays that way, basically if you look at each intermediate layer and consider the pressure on the inside, basically the matter inside has certain pressure, presses out, just like gas in some balloon. There is also pressure coming from outside, And of course, the difference in the pressure, if you wish, the pressure gradient, has to be equal to the amount of the gravity acting on this layer from the inside of the star. And that's pretty much what is called the so-called Tolman-Oppenheimer-Volkow equation. I wrote only a simplified, so-called Neutrino version of it, so it's very simple that you recognize immediately the gravity and everything there. But of course, it gets a little more complicated when you start to introduce some general relativistic corrections. It's slightly more complicated, but the essence remains the same. In order to look at this and analyze how this equation tells you the structure of the star, you actually have to know how the pressure depends with the density of that matter. So in order to calculate pressure here and pressure there, you really need to know at that energy density, if you have so much stuff there, how much pressure it produces. And that's very important theoretical input that unfortunately we only know a little bit about and not very reliable. So of course, in order to extract that information, we can do some observational data, analyze it, and try to reconcile with our predictions. So of course, some of the predictions would be, some of the observational data will be the actual observed masses of the stars, their radii. If that is consistent with our assumption of that equation of state, we can consider also how the matter is made of something and then look at that composition and tell how quickly it cools. And of course, then we would know what if that is consistent with our assumption. We can also consider some deformations of that matter, which can be actually extracted if you consider the so-called mergers of neutron stars. So for example, one of these events gives you very strict constraints of those deformabilities. And what's happening if the two neutron stars start to come too close to each other, they literally start ripping each other there. And during that process, deformations are happening and we start to see how that matter reacts. And from the constraints, you can tell something about this. And of course, there are some generic theoretical limitations. We have to ensure that our theory is causal, that everything is stable. There are many other theoretical constraints that also limit our knowledge about it. So roughly speaking, if we know something like this, how the pressure changes either with number density or energy density, roughly speaking, there are some different forms of description, then pretty much we can predict the structure of the star. Over the years, we had a lot of different information coming up from observations, and the idea is like this. We have some observations. Imagine that I put a random point somewhere here. Each would represent a star. For example, you find a star with the mass 2 solar mass and the radius 12. You put a point here, you put a point there. And basically, when you take a whole sample of the data, you will get sort of like a band of possibilities, and there will be nothing else outside. And then you try to reconcile which of the equation of state work, and then go back and forth and try to constrain this information, and that way constrain your knowledge about the structure of the neutron star. So that's how it works, sort of in a very schematic way. And without going into too many details, because there are people struggling to understand whether there are quark stars or quark cores in the stars for at least 20 years, probably more like 50 years, but about 20 years, there were a couple of exotic observations that were kind of pointing in that direction. Then it was pulled back, then again, back and forth. Information is still not completely stable, I would say. But there are some forms of analysis that are relatively recent that are now pointing even stronger in the direction that the quark matter may be actually existing in the neutron stars. The idea is that the most massive of the stars, they appear to be representing the so-called conformal quark matter equation of state. Without going into too many details, I would say that if you take that perfect relativistic quark matter, you will find some prediction, for example, about the speed of sound, that is squared in the units of the speed of light will be 1/3. And the polytropic index, which is representing essentially the power law, how that pressure depends on the energy density. And in fact, because the conformality means that there are no other unitless parameters that describe that relation. And basically, if there is no unitless parameters, just analyzing the units, you would figure out that pressure has to be proportional to the first power of energy density, and that's what that 1 represents. So considering those observables and analyzing all the data available, this group of people, the paper was published in 2023, came to the conclusion that the most likely conformality measure, they took essentially the square of these two quantities, each of them would be 0 if we had exactly conformal Quark matter, and found that the best probability is actually that this quantity becomes really small after you reach masses roughly 2 solar masses. You could see that here that parameter is very large, and then something suddenly happens and it becomes relatively small. It's clearly not 0, by the way, but it's approaching, it's going in that direction, and there is a qualitative change here happening, and that kind of suggests that the Quark matter does exist in those most massive stars. Qualitative behavior changes around 3 times the saturation density, and if you consider those models, you will roughly find this kind of possibilities for the mass of the Quark core versus the radius, and in some of the stars, those could be reaching up to 7 kilometers in size. So that's essentially very indirect, but very suggestive piece of information that tells us that Quark matter is likely to exist in the heaviest of the stars. There are also some other indirect evidences that we do have some matter that behaves very differently than neutron matter. And to look at that, some people were studying the information about the cooling of the stars. And the cooling of the stars, roughly speaking, would be represented by one of those theoretical curves. There are too many of them, clearly different models, different people, different tastes. But there is some commonality that the observational there is typically laying somewhere a little higher than some of these exotic stars that appear to be way too cold for their young age. So those are the 3 objects that are shown here. Some of them are essentially only 1,000, by the way, 1,000 years for a star is still relatively young. And of course, when you look at that, you will see that they are very cold, and the analysis of the data suggests that the sort of conventional, if you wish, minimal cooling model simply fails to explain that. So there must be, therefore, some exotic matter in those at least stars that explains their faster cooling mechanism. And of course, quark matter is a very natural mechanism for cooling quarks and for cooling stars faster. And I will briefly explain that in a minute. So 2 words about magnetars. I'm not going to go into too many details. There are actually 2 references to 2 very nice reviews that you could check out and read about them. The bottom line is they are strongly magnetized. Typically, it's assumed that the surface magnetic fields are in the range of 10 to 15 Gauss or more, if possible. Notice that this is surface magnetic field. The interior magnetic field is expected to be stronger. Essentially, when the star collapses, you could trace how the magnetic flux goes, and you could assume that the magnetic fields inside could be several orders of magnitude stronger. Probably not approaching 10 to 18 Gauss, because when you start going into so strong magnetic fields, then you will see that the star simply loses its ability to be in that stable configuration that I was showing earlier. Of course, there is a lot of interesting physics I'm not going to touch here. They have some interesting magnetospheres. That magnetosphere leads to very interesting activity. There are a lot of puzzles of what's happening in the surrounding regions around the magnetars. So all of that I'm leaving aside because that's not what I'm going to concentrate on today. Magnetic fields, of course, definitely could affect many of those properties that are relevant for understanding the stars. Clearly, they could modify the equation of state, so how the pressure changes with the energy density. They could change all kinds of thermodynamics, how much heat they carry, how much of that heat can be transferred, what's the conductivity. All of those characteristics could be changed. There could be some interesting feature appearing with respect to the instability. If something develops, for example, very low viscosity, they may start to go into some kind of resonant emitting regime where they become unstable until they lose their orbital momentum or something else. So all of this can be modified. And one of the things that I want to concentrate a little bit more closely on is the cooling of the stars. And I'm not going to go again into all this field because it's essentially a review talk on its own. But generally, if you look at the star, the key concepts that do affect the cooling of the stars are essentially, well, it's like your balance in the bank. How much is there and how much you are spending. Roughly speaking, that's the cooling of the neutron stars. So the composition and the heat capacity of that matter it's made of is one very important ingredient. Essentially, it tells you how much energy you actually carry in the star. Different types of matter have some general behavior that you could understand. For example, normal degenerate matter, some like neutron matter, it will have this specific heat that is scaling with the chemical potential of the neutrons and the temperature. By the way, very similar to what is happening in metals, where this heat capacity will be carried by electrons in a similar way. If you have some gapped phases, for example, if you have a superconducting phase, you would find out that the heat capacity changes radically. It carries this exponential dependence on the temperature when the temperature drops down. And essentially, when you cool it sufficiently low, below the critical temperature, you essentially lose almost all that heat capacity. It doesn't carry much. And that will be important at least at one point in my talk. And the second part, of course, how much you are actually losing of that energy. And there are several different mechanisms of that loss. You emit, well, first of all, you emit photons from the surface of the star. That's like the sun. You see the light coming from the sun and it emits photons. And of course, that carries away the energy. The energy, though, scales as the first power of temperature, Stefan-Boltzmann law, if you wish, proportional to the radius of the surface. If you look at the interior of the star, you will actually find out that's not really as important as the emission coming from the inside of the star itself. Because it has this invisible photons, if you wish, really not photons, neutrinos, that are basically interacting with matter so little that even in the depth of that matter, if you produce one, it pretty much just escapes right away. No matter where you produce it inside, and of course it scales much bigger with the volume, it's proportional to the volume of the star, and of course radius cubed, and that will be a big important factor in the cooling. And of course it scales with the temperature differently for the so-called direct, or if you wish, fast emission processes. It scales as the 6th power of the temperature. For the modified Urca processes, it scales as the 8th power temperature. So at high temperatures, of course, this will be dominating. At the very old age of those stars, perhaps the surface cooling will start to kick in and become competitive. But mostly during the first stages is the neutrino cooling. Of course, it's also very important to understand that there is something here, kind of like a blanket sitting on the surface of the star. Remember that very first layer, outer crust, I told you it's pretty much made of regular nucleons, atoms, nuclei. And because of that, in fact, they are pretty sparse, and in fact, they are looking like essentially an insulator on this very dense, very heat-heavy material, and therefore, it's also kind of keeping it from going through the heat conductivity all the way to the surface right away. So that is very important, especially since this has to be properly modeled before you understand the cooling of the star. Of course, there are some complications as always. There could be mechanisms that are reheating the stars and many other things that I'm not going to go into detail. But the main message I'm going to deliver today is that magnetic field, if it's sufficiently strong, it pretty much affects all of those things. And this brings me to some basic understanding of how that neutrino emission happens. As I said, it's a weak processes. So this is essentially the 2 weak processes that are happening. The closest, simpler process you may know about is the neutron decay. So if you take some neutrons that are coming from atmosphere and they are moving through atmosphere, they actually have a finite lifetime. and in fact they decay, producing proton and electron, and a neutrino. So probably it's closer to this process. But of course, in the quark matter, which is made of two lightest quarks, up and down quark, there will be processes going basically back and forth from U to D and from D to U. When you go from U to D, you capture an electron that is present in the surrounding medium and emit neutrino. In the D to U, you emit back that electron and again emit a neutrino, but now it's anti-neutrino. And those neutrinos, anti-neutrinos, as soon as they are produced, they're gone. Not they are gone, they actually carry away the energy they have. And that's pretty much the mechanism for the cooling. So those are the processes. When you consider this theoretically, you have to be really careful to consider the quark matter carefully. One of the things you have to assume, and not assume, enforce if you wish, that matter has to be electrically neutral. If you allow even a tiny degree of non-neutrality in the medium, you will see that the Coulomb force will be so much it will just rip the star apart. So it's not possible at all. It has to be with high precision electrically neutral. Naively, you will satisfy this condition in many different ways. Notice that the up quark carries the charge 2/3, down quark -1/3, electron -1, so everything's nice. For example, one way to satisfy that is to take twice as many d quarks as u quarks and you will be fine. No electrons are needed. That's too naive though. In fact, there is also the condition of beta equilibrium, which is essentially telling you that the chemical potential between those three types of particles have to be related. In a way, it's related because we have this detailed balance. The reactions from D to U and U to D go with the equal rates. And of course, the balance of the energies in this process is critical. So they have to be essentially satisfying. The rates for the quark matter, those that I just presented diagrams, they were calculated, in fact, more than 40 years ago by Igor. And the emission rate is given by this famous formula. It's not very important to concentrate on details, how that formula looks like. Perhaps only one thing that you previously have seen already is the 6th power of temperature. There are some chemical potentials and many other things. In theory, it's very important to calculate this properly, and there were some attempts to calculate this before Iwamoto, but they were done incorrectly. There is some interesting condensed matter physics, if you wish, entering the calculation, and the calculation can be very easily understood, and the nuanced feature that is very important in the calculation is to appreciate how the conservation of the energy and momentum is satisfied when the particles are forming the so-called Fermi surfaces. So I didn't really go into this, but let me briefly tell you, if you have a lot of neutrons that are forced to be in the lowest possible energy state as a collective state, they have to occupy all different momentum states because they hate each other. Well, I should say they are fermions, so they cannot occupy the same state. But that means that essentially if you start putting those neutrons or quarks in different momentum states, you will end up running out of low momentum states. You will have to put in a higher state, and eventually you form a whole kind of like a sphere of the states in the momentum space, and each of those states have to be occupied up to a certain level, which you call Fermi momentum. And for the energy, it will be the Fermi energy, which is essentially the same as the chemical potential. Anyway, if you start to satisfy that momentum conservation in the case of quarks producing neutrinos, this will be, for example, the conservation when you go from D to U quark and electron and anti-neutrino. And then you have to take into account that what those momenta are in magnitude, I should say. And notice that they are approximately fixed. It's very important why they are fixed, because essentially all the momenta that are sitting for the red represents the U quarks. If you take any point anywhere here inside of this sphere and say this momentum, so there will be kx, ky, kz, and some magnitude, you will see that this will be very far below this edge. And because it's a fermion, there is a Pauli exclusion principle, and that state is essentially kind of like eliminated from any dynamics. It cannot go anywhere a little bit because everything is occupied around it. It's essentially immobilized that way. And the only particles that can do something, change their quantum state, are those sitting close to the edge of this surface. And that's why when you're considering this process, you will have to appreciate that those momenta in magnitude will be fixed very closely to the Fermi momentum. This is, by the way, same that happens in metals. And when you're considering some dynamics in metals, for example, electrical conductivity, you have to deal with that as well. Anyway, it's also important to appreciate the energy scales involved in these processes, and you will appreciate that the temperature of those stars, when we are looking at them and really care about this neutrino cooling, is essentially starting from several MeVs. When it becomes transparent, it kind of drops down. So I'm just saying that temperature is somewhere below 1 MeV or so. The electrical chemical potentials of quarks and electrons, they are fixed by that neutrality and beta equilibrium conditions. And for the quarks, they are pretty large. For the electron, it's not so large, in fact. And you will see that there is this hierarchy of scales. So what? Well, theoretical physicists, they love hierarchies because it leads to good approximations. In this case, the good approximation is that if you look at this momentum, it's so tiny compared to everything else. So if we add momenta this big, and then there is some little like this, maybe it's better to neglect it. And in fact, it is better because it simplifies the analysis a lot. But the thing is, if this surfaces were exactly the radius of the chemical potential, then in fact, all of these three arrows would have to be collinear, basically along the same line. One plus another one equals the third one. But as you could see, I squeezed a little bit the surfaces of the red and blue, the quarks, and that is determined by this so-called Fermi velocity, or theoretically sometimes it's called Fermi liquid corrections, essentially interacting effects in that state of matter. And those correction effects appear to be critical. They, in fact, make sure that they are not collinear, which opens a lot of different possibilities, because essentially you could kind of create a whole ring of states on that blue surface that are open for this process. If they were all collinear, they would point to a single point. And of course, the rates would be miscalculated incorrectly. And in fact, that was what's happening before this historical paper by Igor. So it's a very important, interesting theoretical result. So I wanted to explain to you since it's very easy. But now I'm going to move into what happens if you add magnetic field. When you add magnetic field, the first thing you have to learn that strong magnetic field quantizes the states of those electrons and quarks, pretty much any charged particle that you're going to consider. And instead of regular energy proportional to momentum, maybe momentum times the speed of light, if you are carrying those units, actually, strictly speaking, I dropped some using so-called natural units, and maybe there is a mass, but all of this changes when you have a magnetic field. Instead of states that are pretty much spaced at every point in all of those gray areas, now you actually have only selected quantum states of electrons or quarks in the presence of a strong magnetic field. There is the so-called Landau quantizations, and those are Landau-levels. There is a lot of interesting things about that. I could probably go into another talk just talking about that, but that's not my purpose. My purpose is to tell you that when you do have a lot of them occupying a certain region, you actually, again, fill out all the states up to a certain Fermi level energy. So that's your electron chemical potential if I'm showing the electron quantum states, or quark chemical potential if I'm showing this for the quarks. And as you could see, you have that energy and all the states up to that energy are occupied. Everything above is empty. This is essentially, if you wish, modified Fermi surface. Instead of a ball, you have something a little bit more structured. Maybe I'll have a picture of that in a different way later. And what is important when you're starting to look at this is there is this quantization near that Fermi surface. Everything interesting is happening near this Fermi energy. because all the changes in the states are on the order of 1 MeV, temperature essentially. This depth is tens or hundreds MeV, so essentially all of this is kind of excluded from participation, everything above is empty, and only something in that red belt that is roughly thickness of temperature that is important and participates in the game. When we are considering stars, we have to make sure that those magnetic fields are realistic. So what is realistic for magnetars? I have here a conversion formula. I'm going to write everything in the units of the energy, which is convenient for me since here I'm showing the energy. So if I'm taking the magnetic field, it's natural to convert it into energy squared. And this is the conversion. If we take magnetic field on the order of 10 to 16 Gauss, you will see that this will be on the order of 100 in these units. The important thing when we are considering the actual processes, all those weak processes, you have to know how badly those are discretized, so how far you have to jump from one level to the next. And of course, that will be essentially the separation between the Landau levels. Very, very easy to estimate using this formula. That the separation typically, if you go literally vertical like this, between those levels near the Fermi surface will be approximately of the order EV over mu divided by mu. This is energy squared, this is energy, so if you divide, you will see for the quarks and for the electron, there will be something like this. Actually, I think I lost at least a factor of half or something because I think I didn't take the charge of the quarks to be 1/3 and 2/3. Let's look at 1. So anyway, you'll see that for the quarks, discretization will be kind of negligible. For the electrons, probably not. In fact, there are some additional reasons that because of strong interactions, this will be even less important. I'll leave that aside for now. But what that means that in some of the calculations, it will be justified to neglect the quantization and take this roughly sums over Landau levels into integrals and carefully take into account the quantization of the electrons. That will be important. And now I'm kind of moving into the original part. This is the most technical, but the easiest to comprehend because I only have pictures. So first I'll scare you with the name. There is a famous formalism, formalism that applies to non-equilibrium physics. Here, of course, non-equilibrium fact is that neutrinos escape right after they are produced. The beauty of this is technical. I'm not going to even try to explain, but essentially it's somewhat similar to the kinetic theory, for those who are familiar with that. And performing the calculation, you could actually relate the distribution function or the change of the distribution function of neutrinos to something related to the property of these interactions and diagrams. And that's pretty much what we calculated. That's the actual formula, although something is hidden here. From the conceptual point of view, it's very important to understand that the change of the distribution function pretty much means that you are producing so many neutrinos per unit phase space defined in momentum space. And therefore, if you integrate out with energy or with the momentum they carry, you will get the total energy emitted or the total net momentum emitted along the magnetic field direction. Notice I'm taking z because px, py integrals will give you 0 anyway. There is some sort of symmetry built in because of the magnetic field, all the perpendicular direction kind of equivalent, but z direction is not the equivalent because this is the direction of magnetic field, this is the direction opposite to it. And you could calculate, by the way, this is a different perspective of looking at the Fermi surface when the discretization is included, so you could maybe have a slightly different impression about it. But the bottom line is we did all of this very natural approximations. We neglect quantization of quarks, but fully include the quantization of electrons because it's more important. Of course, definitely take into account those Fermi liquid corrections, and of course include temperature effects exactly. And this is the result. The result is shown in a kind of funny way. Notice I took just the ratio of energy emitted with the magnetic field over the energy emitted without the magnetic field. Roughly speaking, without the magnetic field, what I was explaining, almost the same as Iwamoto with some slightly better improvements in the calculations. And then you will find the results that are behaving something like this. 3 different curves represents 3 different temperatures: temperature close to 0, temperature 0.25 MeV, and temperature 0.5 MeV. And there are several general features you could immediately appreciate. There are some singularities when temperature goes to 0. It's essentially the singularity that represents your chemical potential changing as soon as you start touching the next Landau-level, singularity happens. Then you pass it, go to the next level, again singularity happens. And that's pretty much what this formula represents. In solid-state physics, in two-dimensional solid-state physics, this would be something like a filling factor, how much that Landau-level you filled. It's slight misnomer for three-dimensional physics, but roughly speaking, the physics is the same as you could find in, for example, in metals in magnetic field, how their magnetization changes with magnetic field, or how their heat conductivity changes, many other things related to something like the Alphen effects, where the property is oscillatory and it changes with the magnetic field. Actually, if I plot it inversely as magnetic field, you will see a periodic dependence. Usually that's how experimentally is measured in solid-state physics. And the other feature that you could see as you start increasing temperatures from 0 up, there is some attenuation happens and you have those divergences gone. It gets smoother and smoother approaches. One, when we have 0 magnetic field, clearly because it's divided by that quantity. And then it kind of decreases on average. But as you could see, the change is not that dramatic, maybe 20% or so. So this is one result. It's kind of like a flop. Basically, it's not much of a deal. Maybe the magnetic field will decrease on average the emission by 20%. So what? The other kind of interesting, I think something is missing there. The other interesting thing is that this momentum emission is also non-zero. In fact, I also divided it by energy rate. They have the same units in natural units. Of course, at a 0 magnetic field, there is no momentum emission. Everything is symmetrically, so you have to divide by something else. That's why we use the energy, and it gives you the qualitative measure of how much the momentum is emitted per amount of the energy emitted. And as you could see, it's kind of less than 1% on average. So 1% would be somewhere here.
The peaks of energy and momentum emission match.
Yes, of course, they match. It's the same point where this condition is satisfied.
So at 0 temperature, at the right magnetic field, you have this resonance where the star just
actually, this curve is misleading. Any finite temperature, those become actually attenuated. That's actually, to plot this, I use some kind of ridiculous theoretical approximation that literally takes, in some parts, the temperature to exactly 0. But anyway, the bottom line is this can be calculated in a wider range. Here we went in terms of the more natural Gauss units for the magnetic field. What I was showing there is probably covering only this side, maybe half of this curve. If you push it even harder, larger, stronger fields, you will see something else. In fact, here there will be a strong enhancement. That's when the quantization is extreme. Same for the momentum emission. So all of that can be calculated. So what do we make out of this? Oh, actually, there was some other feature that I didn't emphasize. This momentum emission is not sign determined uniquely. It actually can change with different regimes, could be more in this direction or more in that direction emitting momentum. And one can analyze that very carefully. So here we analyze with respect to which Landau levels of the electrons are contributing the most for different regimes, different temperatures, and all of that. I'm going to skip this. I'm just trying to say simple information that we can analyze in depth each of those processes and know exactly what's happening. We can also analyze how the Fermi-liquid effects become less important, and there is a very simple reason for that. Magnetic field kind of makes the momentum in the perpendicular plane undefined, because in the Landau orbits there is no fixed perpendicular momentum of the electrons. And in fact, that relaxes all of that collinearity condition, and it becomes kind of clear from this analysis that in a strong magnetic field, the difference between results with and without those interaction effects are not that important. So something interesting theoretically, but perhaps not as interesting as this part, because this is where the actual physics that you could kind of think this is beautiful could happen. There was an idea a long time ago, maybe going way longer than 2008, that the neutron stars, if they're strongly magnetized, they could actually emit neutrinos asymmetrically, more one way than the other, and as a result, the momentum will be carried that way. So it's like you are jumping off the boat. You jump this way, boat goes that way. So then how much of that momentum is it enough to explain pulsar wave kicks that we actually observe in supernova planets? And it happens to be this ratio that I was plotting, the ratio of the momentum versus energy emission, that is roughly estimated from numerical data to be something like 2 times 10 negative to the third. And if you compare to the naive predictions before, where people were thinking, well, how much of this polarization is there? Let's just take that as a measure of this ratio. That happens to be actually very large fraction, and in this case, it will be something of the order of 100 to 1,000 times smaller, as the realistic calculation shows. And you could estimate the kick velocity, basically how much of momentum you emit, divide by the density. So this is momentum per unit density, divided by the density. You will find essentially how much of that is emitted. And it's proportional, of course, to this ratio and the specific heat of the matter that you have around. And you could calculate that and estimate that, in fact, unlike this previous old, relatively naive estimates, the actual careful calculation now shows that it's probably at most a few kilometers per second, probably less because they tried to do something super optimistic here. And the actual kicks are on the order of hundreds, and in fact, in sometimes up to 1,000 kilometers per second. So this is definitely not going to work. And I'm probably running out of time. How much time do I have? Okay, I will try to squeeze in one other little detail, and please feel free to stop me whenever you think I'm running out of time. I just wanted to mention briefly something else. There was considering some processes that happen even without magnetic field. I was taking this ratio without magnetic field. Is there anything unique in the present magnetic field that actually will start working as soon as you have sufficiently strong field? And the answer is yes. There is this synchrotron light. Sometimes they emit light. Of course, it's not synchrotron emission. It's essentially emission of similar type when the quark is curved in the magnetic field. As a result, it emits not an actual photon, but so-called virtual photon that goes into neutrino and the neutrino pair. And this process, of course, is very similar to just the standard synchrotron radiation. In fact, in the quantimes regime, I was also looking into that. This was analyzed in all kinds of systems, with exception of quark matter. In fact, all system is an overstatement. It was all kinds of neutron matter, compact matter in compact stars, but everywhere in all of those, it's due to electrons. Because they are the lightest, they're essentially the only ones that contribute. And it wasn't estimated for the quark matter, and some of the conclusions are very promising. They are saying in certain temperature density regimes, this process is actually dominating in nuclear matter. So the question is it the same in quark matter? And that's very much what we reanalyzed carefully recently with my postdoc. We actually calculated the quantity. I'm not going to bore you with the little details, but emphasize that the physics is very easy to understand. Again, essentially is determined by just two parameters. How big is the temperature? So essentially, how big is the width of this red band where the quarks are actually participating in any processes. They are not prohibited from those processes by Pauli blocking. And that's the temperature, because essentially that's how much that region is smeared. So some of the states in this belt are unoccupied below, some above are slightly occupied. and that's what makes it active. The other quantity is the spacing between those levels at that point. So essentially the same quantity I mentioned before. And you could immediately appreciate if the gap is this big and the temperature is this little, those quarks have no chance of jumping from one to the other. They just don't have enough energy. Of course, when the gap is tiny, the temperature is large, a lot of levels around this region start to participate. And that's pretty much all the physics. Everything can be given in terms of this single parameter, the ratio. And you could calculate that and find that essentially for any kind of system of that type, the general formula has this very, very simple appearance. And everything is encoded in one single function that depends on this ratio. That's the function, how it looks like. At some point here, it's 0, v, it approaches a constant. That's where the discretization becomes essentially irrelevant or very little of relevance. And at very large value, the gap large, the rate is exponentially suppressed, as I said, because you simply cannot overcome that big gap with little temperature. So you could also analyze that in the regime of relatively weak magnetic field, when there are a lot of those processes happening, you could classify the processes by the number of the steps or this quanta or this difference between Landau-level indices, how many of them can be crossed, and calculate the distribution of that function as partial contribution for that class of the transitions. And depending on the field, the weaker is the field, you have many Landau levels crossed by those processes. For relatively strong fields, there will be maybe 1 or 2 or 5 steps from one level to the other that are contributing. So all of this can be carefully analyzed, and you could consider, in fact, find that the scaling is such that the maximum always happens roughly around 3 over b. The maximum of this function is scaling with the b. So for those who are dealing with the scaling analysis, they immediately appreciate. So if you divide this by b and then consider the function as function of s times b, you will have some sort of universality, which is obviously seen here. When b becomes smaller and smaller and smaller, it approaches a fixed curve. So all of that can be done. Now coming back to physics, we can plot now. We have the detailed information about the synchrotron emission, mu bar synchrotron emission. And you will find that in quark matter, by the way, as I said, you have to include electrons. The electrons will be not that many. That formula can be solved very easily. You'll find that it's actually less than 0.3% in terms of density electrons. Everything else is quarks. And you will see the contributions given by these curves for relatively small magnetic field, for relatively large magnetic field, for each of those particles. There is some interesting thing. There are so few electrons, but notice how much they're contributed there. There is a very nice explanation. I will leave that for questions if somebody asks. And then you could consider how much it's relevant. And of course, one way of considering the relevance is to divide by the rate that we know is there, that EVA motor rate that we calculated earlier. And unfortunately, you will find that even at the optimal conditions for different magnetic fields, that is still 3 to 4 to maybe even 6 orders of magnitude smaller than EVA motor direct Urca emission rate. So essentially, unlike normal quark matter, normal nuclear matter in certain regimes, this is not contributing a lot to neutrino emission. So essentially, it doesn't modify the cooling. You might feel like I explained you everything about quark matter. You could close the chapter and forget about it. And it's almost true. But the fact is that quark matter may be very interesting as well. In fact, it might be called superconducting. In fact, it's very likely, according to some theoretical predictions, just like regular metals at sufficiently low temperatures, they become superconducting. Quark matter at sufficiently low temperatures, which is not that low actually, could become color superconducting. So what happens then? I briefly mentioned you earlier that if you have some of those fermionic states that are gapped, then the specific heat will be exponentially suppressed. Actually, same happens to neutrino emission, it will be exponentially suppressed. So it seems like there is nothing lost. It's almost true, not completely, because again, quark matter is more interesting than it seems. There could be different types of colorful conducting matter. There are some phases which are made of only U and D quarks, the so-called 2SC or two flavor colors conducting quark matter. In this case, not all quarks actually want to participate in that cooling. In fact, roughly 1 out of 3 will remain ungapped, unpaired, and behave exactly as I explained. And since everything else contributes no heat, no emission, pretty much it will behave the same way. We roughly speaking reduce all the heat capacity by 3, by a factor of 3. We will reduce the emission by the same factor of 3, so nothing changes. Well, there are other possible phases. There is so-called color flavor lock phase, where in fact truly all quarks are gapped, but you have to make sure that its density is sufficiently large that the strange quark is also participating. In this case, of course, that's really exotic. It's like you have a cup, and instead of hot water inside, you have nothing, because it doesn't carry any heat, doesn't emit much. So essentially, you only have the cooling from that outer shell, and in fact, it will be not changing the regular nuclear matter cooling mechanism, provided that layer is sufficiently deep. If it's very shallow, pretty much it will cool down very quickly and be cool all the time. There are also some more exotic phases. Again, I don't want to go into any details, just point out that there are some other possibilities where, unfortunately, the answer is less trivial because there are so-called gapless phases where the gaps appear not across the whole Fermi surface, so roughly speaking, not all of the states are blocked, but there are some points, nodes, or lines where something is like regular nuclear matter or regular quark matter, everywhere else is gapped. What happens there, it's completely unclear because it depends on the geometry of the system, the magnetic field direction, and many other things. So that brings me to my conclusion. The main message is actually here, and that's it. That what I wanted to say that quark matter and very strong magnetic field may exist in the stars and may have observational features. And that's pretty much the main message. If you insist on going to some sort of key steps, key details that I tried to explain, is that the quark matter cools very rapidly and the magnetic field affects that relatively moderately. The direct Urca emission, of course, is asymmetric, but unlike the previous predictions, in fact, some of those predictions are not just as old as 2008. There were repetitions of similar idea going just only 2 years ago. So all of that, unfortunately, is not true. Now we know that this momentum emission is not sufficiently strong to provide any sizable pulse fields. Compared to those Urca processes, synchrotron emission is unique, is very qualitatively interesting, but unfortunately, it's not contributing much to cooling of quark matter. Superconducting states are a completely separate story. I didn't really go into details, but there are still some puzzles remaining, and one potentially could resolve them in the future. And that would be related to perhaps some exotic phases, less to this standard phases. And with that, I'll stop. I'll flash this slide with the list of some reviews that I found interesting and useful. Perhaps you will benefit from them.
Preguntas. Orlando.
In the Quark Cores Emission, there is a difference between neutrinos and analog particles.
Not really. We are talking about the energies much, much larger than their masses. And I don't think any of these weak processes will change the rate dramatically enough to be of big relevance, unless I'm missing something deeper than I understand. By the way, if it's major related, I completely neglected neutrino masses because compared to those typical temperatures, they are tiny.
Further questions?
If not, can you explain about the electrons that you said? That there is a very nice explanation in one of the slides.
Oh, yes.
You skipped it.
In one of those things, I was telling you that the rate due to emission of those very, very few electrons. So imagine that you have like 3 electrons for each 1,000 of quarks. And yet, when you go to sufficiently high temperature here, you will see that the rate of those few electrons produce pretty much as much, in fact, more emission, synchrotron emission, than the quarks. And the funny thing is like this. Generically, if you have a lot of states sitting on the Fermi surface, it's basically you counting the number of those states that are actually active and participate in the process. And naively, you would say, it's proportional to the size of this object, size of this sphere, mu squared. Mu is representing the energy. So for the electrons, it's 50 squared. For the quarks, it's 300 squared. So huge difference. So you would say it should be so many more neutrinos emitted from the quarks. The problem is that, in fact, the emission rate happens to be exactly inversely proportional to the momentum or the energy they are momentum they are carrying. So essentially proportional to mu squared divided by mu squared. So there are fewer electrons, but they are emitting proportionally much stronger, and therefore they compete quite well. But of course, because of that competition and the discretization, it happens much later in terms of temperature. But that's the essence of it. I must say it's not our discovery. It's actually going back to those other studies on regular nuclear matter and other forms of matter where electrons dominate. Even there, they realized that there is this puzzling feature that it's not proportional to the chemical potential of electrons squared, as naively you would expect from the Fermi surface and sort of naive expectations. They didn't give much of explanation, I should say. But I think if you read carefully and you understand that those are Russian authors, you know that sometimes they not say everything they know. So it was clear that they understood it, but they kind of left it as a puzzle.
Cool, thank you. Questions? Preguntas?
Thanks. So the neutrinos produced this way, do they follow a Fermi-Dirac distribution, or this spectrum is much more complicated than that?
Actually, they do have the distribution which is roughly Fermi-Dirac. It's absolutely true. It's not Fermi-Dirac because, strictly speaking, I have to look, there is potentially some power of energy in front and then Fermi-Dirac distribution.
Okay, and another quick question. You mentioned there's a correction on the neutrino self-energy. Does it make an effective neutrino mass inside the matter?
No, not in this context. I don't think it was providing any non-zero neutrino mass. But in all honesty, I wasn't really considering the real part of that at all. That's obviously a question from an expert. Where is that? I'm not sure if I even showed the diagram. But, well, actually I should. Yeah. This one. So there is something for the experts. I put this cross line across this diagram. Roughly speaking, it means like cutting it, extracting the imaginary part. And when you cut it, you kind of appreciate, just close the right-hand side. You will see that essentially the same process that are shown there. So I'm not even looking at the real part. I was actually concentrating on the imaginary part of this.
I was just wondering if that changed the dynamics somehow.
Well, not really, no. The effects, the actual sort of self-energy effects in the real part is tiny. If they do give any mass, that mass is way, way below the temperature. So Majorana mass, Dirac mass, some self-consistent, dynamically generated, it's going to be kind of negligible for this purposes at least.
Anything else?
I have a question. Is the neutron star sort of rigid when it's rotating, or it's a rotating liquid? It's worth something.
Right. Naively, it is rigid. Naively. Of course, because in many cases it's relatively strong interactions, and the star is living for a very long time, and naively any differential rotation should have more than enough time to cease, to dissipate. But in principle, when something dramatic starts to happen, like mergers, then of course all this starts to be real questions. So under sort of normal conditions, nothing. But if you go into R mode resonance or something else, there could be some problems developing.
In one of your slides appears the strong coupling of S. And then in the calculations, you have used any expression for this alpha S that depends on the magnetic field, the temperature.
Right.
What is the value of the alpha S?
Yeah, this is a Hilo kind of question. There is no good number for that. So all the people are taking something reasonable. Let's say something between 0.3 and 1. The thing is, it doesn't change anything, truly. What it does change is that we do know that this effect exists and the Fermi surface is kind of squeezed a little bit. How much is squeezed? You could actually take it as a Fudge parameter, strictly speaking, and don't care too much about it, because essentially, in the end, it's expected to be small. So you're not expecting that that quark matter Fermi surface kind of goes down by a factor of 2 or 5 or something. It's a small effect. And essentially, that's the only thing that matters. In the rate itself, that's where it shows up. So essentially, you're training this small parameter alpha S is sitting here instead of some higher power temperature there. And if you introduce the higher power temperature there, it's going to be really much more dramatic effect. So we know that this effect exists, but you could think of this as some Fudge factor. In fact, this formula is not correct, by the way. This formula is obtained in certain approximation.
For describing quark matter.
No, it's a good approximation for describing quark matter. But even in this framework, exactly as described here, if you carefully calculate it without doing some approximations in the integrals, in fact, there will be yet additional constant, which may be a factor of 2. And it will depend on the ratio of temperature and electrochemical potential in this particular problem most sensitively. And there are all kinds of improvements. There are also non-Fermi liquid corrections that Thomas Schaefer and Kai Franzer were estimating, and they also give some corrections. But at the end of the day, our experimental, observational, if you wish, knowledge is so limited that no matter what I put here, it's pretty much not making any difference. So instead of cooling, let's say in 2 days, it will cool in 3 days. That's pretty much the differences we're talking about.
Your last question? If not, let's thank Igor again.